Hello, my name is Junze. I'm a student at Boston University. Today, I'm going to present a linearly optimal bound for fast regression with L infinity guarantee. This is a joint work with Zhao from Adobe Research and with Mingquan Ye from the University of Illinois at Chicago and with Lichen Zhang from MIT. This is the table of content of this presentation. First, I'm going to present the background and our goals. Then I'm going to present our motivations. And after that, I'm going to present our main result. And finally, I will present the specific techniques we use for proving our main results. Linear regression is an important model in machine learning and statistics. The purpose is to optimize the following problem is to find the minimum of the L2 norm of AX minus B, where A is a matrix, X and B are two vectors. By minimizing this L2 norm, we can find the vector X that results in the smallest possible discrepancy between the predicted value and the actual observed value. This is a problem we study. We are given a matrix A and a vector B. We consider the regression problem with L infinity guarantee, namely to find the vector X prime such that X prime minus X star is bounded. And X star is the exact solution of the linear regression problem, and X prime is the approximated solution. In this session, we present two basic definitions. The first one is subsample randomized Hadamard transform. The SRHT matrix S is defined as S is equal to 1 over the square root of M times P times H times D, where M is the number of rows of the matrix S. P, H, and D are three matrices. The matrix P satisfies that each row of it contains exactly one at a random position. H is the n by n Hadamard matrix, and D is the n by n diagonal matrix, with each diagonal entry being a value in either -1 or +1 with equal probability. And the second definition is oblivious subspace embedding. We define OSE as follows. Pi is a distribution on M times N matrix, and U is an orthonormal basis. A matrix S drawn from the distribution pi has the property that the singular values of SU lies in the range from 1 minus epsilon to 1 plus epsilon. When the matrix S satisfies the oblivious subspace embedding property, one can show that the approximate solution X prime is close to X star in the L2 sense, namely the L2 norm of X prime minus X star is bounded. However, L2 closeness does not characterize how good X prime approximates X star, because X star can have a good spread of its L2 mass over all coordinates, whereas X prime might concentrate its mass over a few coordinates. Formally speaking, if we let A to be a vector, and one can measure how far the inner product between A and X prime deviates from A and X star through the following equation. And our motivation to improve this bound is to make linear regression model more applicable to large, complex, and nonlinear model, such as linear regression has relationship with the second order method for training neural network and with the convex optimization. Now I'm going to present our main result. We let A to be a matrix and B to be a vector. We let S to be an SRHT matrix with M rows. And for any arbitrary vector A, we can show that the absolute value between the inner product between A and X star and the inner product between A and X prime, this is bounded by the right-hand side of the equation, namely the epsilon over the square root of D times L2 norm of A times the L2 norm of AXR minus B times the spectral norm of the pseudo inverse of the matrix A. And this holds with probability 1 minus delta. In other words, we improved the previous bound by the new bound. Like previous bound was O of epsilon, and we improve it to epsilon over the square root of D. Now I'm going to present the techniques for proving our main result. First, I will present the definition of OCE. So we say a randomized matrix S satisfy OCE if the following equation hold. And the distribution pi is oblivious to any fixed vector G and H. Our techniques involve to show that the S satisfy the OSE property and the OCE property. The SRHT matrix S satisfy OSE can be drawn from the lemmas from the previous work. And in this paper, we prove that S can satisfy OCE. Thus, it suffices to show that the OCE and OSE combined together will imply our main result. For any fixed vector A and B satisfying U transpose times B is equal to 0, we can show the following equation. Then the rest of the thing is just to choose M, which is greater than epsilon to the -2 times D times beta to the second power, which is greater than epsilon to the -2 times D times the logarithm of n over delta to the third power. If M is greater than this, then it gives us the OSE property, which implies that M is greater than the epsilon over -2 times D times the logarithm of n over delta to the third power. Thank you for watching. This is our works cited page.